All right. So the chat, I guess, in preparation for the Propagation Summit. What's that? Next weekend? Yeah. So this is a primer for it, I guess. It was uncoordinated, but I'm going to be talking about the ionosphere, space weather, and amateur radio. And more importantly, I want to give some credit to folks before I get into this. So I want to first thank NA5N, who was very gracious. I was trying to get that individual to give this presentation, but he was not able to make it. So he allowed me to use a lot of his materials, which I have. I'd also like to thank John, N4TOL, and Mike for taking a look at the presentation and give me some feedback to help keep it between the rails. So with that, let me get into the presentation. So we've all had experiences on the bands where we've had amazing DX contacts, and then other times when the bands just weren't cooperating, and no matter what we tried to do, it seemed like we just couldn't make it down to the end of the street, much less cross the state or to NADX. And assuming that our gear was working properly, it's likely skywave propagation that either allowed us or prevented us from making successful contacts. I'm going to talk about the ionosphere, some of the effects that affect ionospheric communications, the sources of space weather phenomenon, and I'll wrap it up with how to use tools to predict what the ionosphere is going to do and help you make contacts. So, excuse me. So, skywave propagation. So anytime signal enters the ionosphere, several things may happen. It could be attenuated, refracted, or go straight through and out into outer space. If it makes it into the ionospheric region and there's refraction, or refraction will occur for signals that are below this certain, air quotes, critical frequency. That's just below, that critical frequency is just below those that go straight through and past the ionosphere. So the vast majority of our long distance communication in the HF region is a result of skywave propagation. And I want to introduce a term here, which is refraction. It's not reflection, it's refraction. It's the change in direction of a wave passing from one medium to another. Those of us that wear glasses are very familiar with that. Or it's a gradual change in medium density. So a little bit about our ionosphere. As you can see, I've got this diagram on the right-hand side of your screen, and it's in kilometers. But if you notice down towards the bottom, and I don't know what the size of your screen is, but I've got an image of a 747, and just above that, up at the 25-kilometer range, is the SR-71, highest flying aircraft that we've had, and that puts our ionosphere kind of in perspective. So we're at the very end, the 1% down at the bottom. That's where we inhabit. So this area that we call the ionosphere is where the magic happens, right? Signals that get up there, or most of the signals that get up there, manage to get refracted back to Earth. So on to the next slide. Now from the ground level, the other day I was out walking about and I saw this contrail, and it occurred to me that aircraft, although I can't see it, I know it's there because of the contrail. It's about 5 miles up. You take that, multiply it by 8 times, and you're at the bottom of the D layer. Just put things into people perspective. The F layer is 28 times higher than that, or at least the bottom of it. So it's 28 to 30 times higher than that aircraft. So it kind of puts things into perspective of just how high the ionosphere is. So what is the ionosphere? So it's set about an altitude of 40 miles and above. Solar radiation, primarily ultraviolet rays, strike the tenuous atmosphere up there and manage to knock off the outer electrons of various gases and or gaseous atoms and molecules that are up there. And in doing so, it frees the electron, and that electron now has a whopping temperature of roughly 2,000 degrees Fahrenheit, which is to say that the ionosphere is really a plasma. And on top of that, it's electrically conductive. So I've got a somewhat complicated chart. On the left-hand side of the chart, you see the squiggly line that all of a sudden takes a right angle and then goes vertical. So that's our temperature gradient. So at Earth level, we're down in the temperatures that we normally experience. As you start getting into the troposphere, the stratosphere, and the mesosphere, temperatures are fairly cold. They get down into the minus 50s, minus 60s, et cetera. But suddenly when we get to this point where we start getting bombarded by ultraviolet rays, see that the temperature takes off, and that's the source of our plasma. So what's the big deal with plasma? Well, radio waves interact with the plasma. So in general, radio signals that are less than 40 megahertz tend to get refracted back towards Earth. Signals that are above 40 megahertz, they tend to go through the ionosphere and go off into space. That's not necessarily a bad thing, because that enables satellite communication, communication with the ISS, radio astronomy, et cetera. However, the ionosphere's reflective effectiveness, it depends upon the number of free electrons that are available, and that's what drives our critical frequency, the frequency of the transmitted signal, and the incident angle of that radio signal into the ionosphere. And we'll explore these a little bit further as we go along. So what's this critical frequency, right? As I said, it's a plasma up there, and the plasma, depending on the number of free electrons in it, it varies its resonance frequency. And for those of you associated with music, think of an instrument that you tune. On a guitar, you put more tension on it, it changes the frequency at which that chord resonates. And in a rough analogy, the plasma, the more electrons that are present, you're going to have a higher resonating frequency, which means that it can act it'll have a higher critical frequency and allow a higher frequency signal to be refracted back to Earth. So critical frequencies change throughout the day, depending on the radiation of the sun, the number of electron densities, what the atmospheric conditions is, what the speed of the winds are, and there's a number of other things in here. So how do we know about the ionosphere and what's going on up there? Well, we have this device. It's essentially a upward-looking radar that has a varying amplitude to it, and it performs, or it does an iosonde. Basically, it sends a signal up into the ionosphere and looks for its return. And what that does is two things. The first one is based on the frequency that gets returned to the ground. That tells us, our critical frequency. And then by the timing of the signal to go hit the ionosphere and come back, it gives us the height. And those are two things that we use to enhance our DX. Just as a side note, I've got electron density, and that's also another way of determining what our critical frequency is, but it's just much easier to beam a signal up and wait for its return. than to send a rocket up and try and count the number of free electrons per cubic meter. Anyways, so over here on the right-hand side, I have a picture of an ionogram. That's the output of an ionosonde. And you can see the frequencies at which we bounce off the ionosphere. 1, 2, 3 megahertz, or 1, 2.5 megahertz comes right back at us at 100 kilometers. Then I have to move this screen because I can't see the rest of this. So as we go up in frequency, the signal penetrates further into the ionosphere before being reflected back. So these become our critical frequencies for the various ionospheric levels, the E, F1, F2 ranges. And this is important because critical frequency is used in our to calculate our maximum usable frequency, which is coming up next. So the maximum usable frequency is really that frequency which about half the time, 50% of the time, it tells us or it indicates when we have propagation between any 2 points. Not only that, so one of the things that happens, right, I mentioned that the radio waves get refracted back to Earth. So if we shoot them straight up, well, they've got to do a 180-degree bend to come back down. However, if we have an oblique angle, if we help them along by leaning into the ionosphere instead of going straight up, it's going to make or allow for signals to be refracted at higher frequencies. And it just so happens that we have this nifty little equation here that helps us with that. So if I have an angle, a signal coming into the ionosphere, I take my critical frequency, which is found from the vertical firing radar and is readily available on the internet, and I divide it by the cosine of this angle, and it tells me what my maximum usable frequency is. So on my previous chart, I showed here that for this electron density, 1 times 10 to the 12th electrons per cubic meter, corresponds to roughly 9 megahertz as a critical frequency. I take that critical frequency, 9 megahertz, and I divide it by the incident angle, and I'm assuming that in this case it's 52 degrees, and I'll cover this more in detail as we go further. If that's in fact the angle that's intersecting with the ionosphere, then my maximum usable frequency, instead of being 9 megahertz, now increases to a whopping almost 15 megahertz. So now 20 meters is open. Woohoo! But as I said, this accounts for roughly half the number of days propagations available. So there's another concept called optimum working frequency. And as a rule of thumb, take 20% of our maximum usable frequency, and this will bump up our ability to make a contact between 2 points and figure out what the maximal usable frequency is by dividing it by or multiplying by 0.8. All right, so any questions at this point? Checking my speaker. All right, not hearing anything. All right, so maximum usable frequency and angle of radiation from coming off of the antenna. So we can do, it depends on what we're trying to do, right? If we're trying to achieve dx, we want to lean that angle as much as possible and have it skip off the ionosphere, similar to the way we skip stones off of a lake. And to do so, we would want to use an antenna that has a relatively low firing angle. Whereas if we're trying to work local contacts, whether it be tactical, ARES, or just local area ragchu on FM, HF, then we'd want something that goes vertical and comes straight back down. We don't want the signal going all over the place. So we would use an antenna that would generally fire straight up as opposed one that leans the firing angle into the ionosphere. So what this does is, if I lean the signal and I'm skipping off the ionosphere, it allows me to use a higher frequency based on the formula critical frequency divided by the incident angle. Whereas in near vertical incidence skywave, what ends up happening is my maximum operating frequency is going to be pretty dang close to critical frequency. So if my critical frequency is 9 megahertz, that's going to be my maximum operating frequency. If I go beyond that, if I try to send a 14 megahertz 14 megahertz signal straight up and down, it's going to go straight through the ionosphere. It's not going to bounce back. Any questions? Okay.
Yes, I have a question, Jim. Can you go back over alpha, the incidence angle, and cosine alpha? And when would you, as a ham operator, when would you see that referenced? I don't think I've ever seen a reference to alpha.
Let me go back to the slide alpha. So alpha is the incident angle. And so it's not a simple trigonometric function. You need, because the Earth and the ionosphere is curved. But basically what you're trying to do is, if you're firing the signal, let's say along the horizon, and let me just take I did bring up a slide for that. I believe this is it. Yep. All right. So if you have a signal and you shoot it parallel to the horizon and assume that you don't have any losses due to ground clutter, that signal would travel almost 2,200 kilometers before it intersected with the ionosphere. And so what we're trying to do is determine in this particular example, I was trying to figure out what our maximum angle was. And it depends on the height of the ionosphere, but it's roughly 70 degrees or so. And you look at the angle that an antenna's main lobe projects the signal at, and it's rarely is it level. It's usually 15, 20 degrees or so, at best, sometimes 45 or more. So what that would do is that determines that angle. And if you give me a second, Joe, let me go back to, oops. So yeah, you jumped one slide ahead of me, Joe. Let me get back to your answer.
Yeah, I'm sorry. I don't mean to interrupt the flow.
No, not a problem. But it's a good question. It's a valid question, and I'll answer it in just a second.
Yeah, thank you.
So
Jim, we got one more question that's related to this, and that would be Matt Allison's asking what the incidence angle. He's making a statement that says it's the takeoff angle of your signal, and then he has questioning, right?
It's pretty close. It's pretty close. All right. So as you get into it, so if you're dealing with a simple trigonometric function where you have a right angle, yeah, it's easy to calculate. But once you start getting into higher angles of elevation, then you have to use the law of sines to compute this. And it's not exact opposite of, well, all angles have to add up to 180 degrees. All angles have to add up to 180 degrees. So it's close to to 90 minus that angle. But it's somewhere around, the incident angle is somewhere around 60 degrees plus or minus 5, all the way up to 90 degrees for vertical incidence propagation. So that's about as good as you're going to get. If you can get 60 degrees, you're going to get max dx, and assuming that you have a ionospheric level at, say, 320 kilometers of altitude, you're going to get, your first hop is going to be at 4,000 miles, and I'll explain that next. So anyways, let me just address quickly. We've got these three main layers. We have the D layer. This is relatively low elevation. It's 35 to 55 miles in altitude. It vanishes at night, but the principal characteristic of the D layer is that it attenuates signals, especially the lower frequency or longer wavelength signals. 160 meters does not propagate at all through the D layer. 20 meters will punch through it, but so that the lower you get in frequency, or the longer the wavelength is, the poorer it performs in the D layer. The E layer, 55 to 95 miles in altitude. This thing normally reflects 10 megahertz and below, and it fades rather quickly at nighttime. The last to talk, we have the F1 and F2, but for all practical purposes, it's the F layer that's anywhere between 95 and 320 miles of altitude, and normally reflects waves lower than 40 megahertz. If we have significant excitation in the ionosphere, that frequency might increase to up to 6 meters or more, but typically not. And the F2 layer, the uppermost layer, that one is a persistent layer, meaning it's present at night. At nighttime, it loses about an order of magnitude in the electron density, meaning it doesn't handle high frequencies as well as it does in the daytime. However, the electrons that, the free electrons that are present at nighttime are due to the high altitude winds that are blowing electrons over from the daylight side of the planet. The fact that it's the outermost ion layer means that it's especially impacted by space weather, which makes prediction a little bit of a pickle. So now to answer Joe's question, I'm putting angle of departure, ionospheric layer, and band usage in one particular slide. So I want to look specifically at first hop. So let's assume that our F2 layer is at 320 kilometers. Our E layer is at 105 kilometers. And I have two fictitious antennas, one that all signals come off of it at 45 degrees, and the other one that all signals come off at 16 degrees. So I'm going to plot these against this curve, which is to the other person asking a question, what the elevation angle of your antenna is. And this one's corrected for, it's not looking at the incident angle on the ionosphere, it's looking at the takeoff angle on the ground. So the first case, let's suppose that our antenna has a firing angle of 45 degrees. That means that the bulk of the radiating lobe on an azimuth scale is at 45 degrees. So assuming that this magic antenna is tuned to 40 meters, what I will do is I'll look at 45 degrees on this chart. And since 40 megahertz, 40 meters is 7 megahertz, it's below that 10 megahertz limit for the E band that I mentioned earlier. So it's going to bounce off of the E band. And since it's bouncing off the E-band, I want to go to the first hop E-band curve. So 45 degrees, I go to the first hop E-band and then go straight down, and it tells me that the first hop is going to be roughly 200 kilometers. Now, if I managed to retune this magic antenna to where it was doing 20 megahertz, or 20 meters, 14 megahertz, then let's take that same firing angle, 45 degrees, but instead of bouncing off the E layer, because now I'm at a higher frequency, it penetrates through the E layer and bounces off the F layer, and that first hop for the F layer is going to put my signal at 600 kilometers. So, Joe, this goes to what you were talking about. Now, if I manage to lower, I swap out antennas and I get this new Wamperdiner antenna that fires at a lower angle and gets closer to the ground and is able to come in at a shallower angle into the ionosphere, then if I follow my 40 meter or 7 megahertz trend, right, let's say it's 16 megahertz, and I go to the first hop, the E layer, at on a 40 meter signal, that comes down to around 680 kilometers. But if I manage to jack up the frequency and I'm transmitting on 20 meters, which is 14 megahertz, punches through that E layer, bounces off the F layer. So now I take it off to bounce it off the F curve, first hop F curve, and that's almost 1,800 kilometers. And I circle these two in light blue, and this is that example that I was showing. If you could send a signal that was parallel to the ground and eventually made it out to the, without losing any signal, again, a magic signal that started off parallel to the ground, there was no loss till it got out to the ionosphere and back and bounced or refracted, back to the ground, we'd have a whopping 4,000 kilometers as our maximum for top. So hopefully this answered some of your questions, Joe.
Thank you. Yes, indeed. Thank you, Jim.
All right. So I just want to point out something here. Let's say that, so if you look at these 2 points right here, 600 and 680 kilometers roughly, they're pretty close. There's probably, based on the thickness of the lobe, a little bit of overlap. So I could, if I wanted to talk to somebody who happens to be exactly at this distance from my QTH, and the atmosphere and ionosphere is all behaving correctly, which would I rather do? Would I rather do a 2-hop signal, go up through the ionosphere, go up through the E layer, bounce off the F layer or E layer, come back through the D layer, hit the ground, go back up through the DE and back down? Or would I rather just do 1 hop, go through that once instead of twice? The answer is I'd rather do it once, right? So that's the benefit of the lower angle. And the reason for that is that D layer is an attenuation layer. And every time I go through it, whether it's going up or down or multiple hops, every time I go through that D layer, there's some attenuation on the signal. And at some point, it vanishes. So if you can maximize your distance on 1 hop, better. There's obviously disadvantage to this, because if you have a narrow beam, then what's going to end up happening, if you have an incident angle that is above that lobe, you may not hear the other contact. So there's pros and cons to having high fire and low firing antennas. So that's the basics of the ionosphere. So there's the altitude, there's the angles, there's the layers and what they refract, etc. But as I mentioned earlier, that there's difficulties predicting what the ionosphere is going to do because of space factors. They influence the ionosphere's behavior and in turn affect radio propagation. So I want to explore some of these in the next series of slides. And there's three main factors to look at. The first one is solar flux. The second one is ionospheric disturbances. And wrapping it up is geomagnetic disturbances. So let's look into solar flux first. So the sun, and more importantly, the sunspots have intense magnetic activity. And that magnetic activity is focused right here in what's called the umbra. Around the penumbra, you have a number of electrons that are being accelerated by this strong magnetic field in the umbra in the center of the sunspot. And when these collide with neutral atoms, they suddenly come to a stop. Excuse me. That's it's called bremsstrahlung, and it generates an intense amount of cosmic or hard X-rays, soft X-rays, and ultraviolet rays. And this is what ionizes the outer layers of our atmosphere. So the more sunspots we have, the more ionization or the more X-rays and ultraviolet radiation is present to ionize our atmosphere. So bottom line, more sunspots, more flux, higher maximum user frequency. And just to give you a perspective of these things, I mean, this is an outline of the US, fits inside one of these sunspots. Each one of these bubbles or granulations on the sun could be the size of Texas or Alaska or both combined. So solar flux, how do we find out about it? How do we use it? So fortunately, NOAA and several other organizations publish space weather information. And if you go to the geophysical alert text, it'll tell you what today's solar flux is. This was on Christmas Day. The solar flux was 88. And in general, if our solar flux is less than 100, we're going to have not so great propagation. However, if it's over 150, we're going to have outstanding propagation. As a general rule of thumb, anything over 100, if 10 meters is open, solar propagation or solar flux is over 150. And you don't have to jot down this cryptic URL. Just go to your whatever browser you have, type in solar flux index today, and it'll take you, if not to this page, to a similar page that gives you what the solar flux is. And I'll further on, I'll explain how we use the solar flux. So the next thing that I want to talk about is ionospheric disturbances. So the solar flux, right? We know that the sun has a 11-year cycle. As the sunspots increase, so does our ability to communicate due to the solar flux. But the sun also has a nasty tendency to belch every now and then. And when it does so, it's usually in the form of flares. They call them sudden ionospheric disturbances, but it's really generating a significant amount of X-rays and extreme ultraviolet radiation. So what this does is causes a very high ionization and plasma density in the D region. And if you recall, I mentioned that the D region is one of attenuation. So if it gets high enough, if the ionization in the D region gets high enough, it can actually lead to radio blackouts. So we have, is one of the prognostic it's space weather indicators is solar ray flux. And as you can see, they're classified as A, B, and C. flares, and these are pretty much benign. However, when you get into the M and X class flares, these are the ones that can cause perturbations on our ionosphere and lead to radio blackouts. So for those of you who do QRP and just anybody who's doing contesting, if you happen to be in a contest, when you have one of these ionospheric disturbances, basically a flare, and you experience a blackout, don't turn off your gear and walk away. Take a break, get a sandwich, go take a walk, stretch your legs, whatever. But what's going to happen is within the hour after this blast of X-rays is energized our ionosphere, the D layer is going to go back to, is going to reduce in density, allowing signals to pass through. But what's also going to happen is the E and F layers are going to become highly energized, and the maximum music frequency is going to climb significantly. So at that point, you might be able to work southern Somalia on 10 meters on a good day. So it's just an operating hint. There's a silver lining to all of this. So let me go in and finally talk about geomagnetic disturbances. So I mentioned earlier that every now and then the sun belches and sends out a flare or a solar flare. Along with that are a number of charged particles. So, well, hang on, let me back up a little bit. I wanted to show you something. Where is it? Yep. So, yeah, I wanted to show you this video. I think it's pretty impressive. It'll give you a perspective on the power of these X-ray or these sudden ionospheric disturbances. Where are we? Here we are. All right. Hopefully you can see this.
So Jim, while your video is running, I don't think your audio is working. So you might want to just hang on a minute.
Can anybody lip read?
We'll have him go back over it in a minute.
Can't hear you.
Hang on, we'll fix this.
Jim, we lost your audio.
You want to pick it up, Mike, and take it from here?
Yeah, when the sun comes out, it gets light. When the sun goes, Earth turns around, it gets dark. And there's this gray line that's in between, and the D layer does stay active except when it gets to the gray line, and then it drops out. That's about it.
You can send
However,
Jim home now.
You just hang on a second. We'll get a hold of Jim here. And
I expect him to repeat everything he said since he went silent.
That's what we're gonna make him do. I mean,
He's on a roll there. You
He
might
is.
not get his get his attention.
and now he's looking at his phone and he's saying that it's me. Hey, you lost your audio. When you turn your video on, your audio disappeared. So everybody on the meeting wants you to repeat everything from the start of the video verbatim.
If he doesn't repeat it, I want my money back.
And they want their money back if you can't repeat it all. So I don't know why. It says you're not muted. So I don't know why you lost your audio. Must have been something that you're in. Okay.
Well, now Jim can say everything in the phone mic and you can repeat it all.
Well, we can do, and so
I'm
here-
sorry, that's not an acceptable substitute. No,
What do you
no, no,
mean?
no, it's gotta be Jim.
Hey, Jim, here's what's gonna happen. You're gonna talk on the phone. I'm gonna hold the phone up to the computer and we're gonna acoustic couple into Zoom. This is just, how technology works.
Does anybody have a digipeater?
Okay. Yeah, go ahead. Yep. We'll go from there. Okay. All right, so Jim is gonna stop sharing and reset his audio, and then he's gonna see what happens. The acoustic coupling concept probably would have worked, but right now we have
One little comment I thought it occurred to me, but I didn't want to interrupt is the ISS is about 400 kilometers or 250 miles. So just to give you a little perspective, it's right at the edge of the top of the F layer. I thought that was kind of interesting. It just puts it again in perspective,
that is interesting.
I guess that's why it slows up all the time and has to reboot itself back up into orbit, huh?
According to my just checking it out, I think it stays at right around 254 miles above Earth. They try to keep it at that around that level. I don't know what the up and down tolerance is. It's not zero, but it's pretty close to that level all the time.
All right, here he comes.
Tell Zoom we want our money back.
You have to speak to the Chinese to process that request.
They're listening now, so they should handle it.
Seriously, everything that goes through Zoom, they get.
All right, so Jim's back in.
I just read his lips and I don't like what he said.
We have to use the acoustic coupling.
Thing in my corner up here says turn on original sound up there in the corner by recording.
You want to go with the acoustic coupling? All right. Okay, let's try it. Go ahead.
That's really, really low on some of our ends.
Really low. Really low.
He could probably dial into the meeting using his phone.
Yeah. You want to try dialing in with your phone?
So how's this?
That's much
There we
better.
go.
There you go. You're 5 by 9.
He's back.
All right. Okay, so no more videos. Video is bad.
All right, you want to go back to the screen?
Yeah.
You should be able to share.
Great.
There you go.
So, okay. All right.
I have a question. Was that video real time or was that time lapse or something?
It was real. Well, actually, I don't know, Jim.
Well, it was impressive anyway, but I mean, it's just very interesting, but I didn't know if it was happening, you know, as it appeared or if that was some kind of a time lapse, but it doesn't really matter. It's very impressive.
Right, just the amount of raw energy. So the other, let me get over to where I was in geomagnetic disturbances. So the other video that I wanted to show you was, and I don't dare do it because I don't want my sound to go away. But basically, it was a kind of like a stereo image of the solar winds as one of these flares came off, and you could clearly see the solar skirt flailing around the sun. And what this does, so back to what geomagnetic storms do, is that they alter or affect the Earth's magnetic field, and the supersonic particles that are coming off the flare end up colliding with our magnetic sphere, creating large amounts of noise. So, and this is measured using the K or the AP index. And the P is a subset for planetary, meaning it's an average of multiple stations around the world measuring our magnetosphere or distortions in the magnetosphere. So these indices indicate a relative amount of noise that you would hear on HF if we were experiencing one of these events. If we were having a full-blown storm, we would have very high noise levels, or in some case, in severe storms, just blackout to prevent that, keep us from having any propagation at all. So let's put all this together. I talked about the solar flare, the sunspot, the solar flares, and the geomagnetic storms. So what I wanted to focus on is this this graph, and along this axis, this is in days. So if the solar flare occurs at this point in time, this first tick would be 1 day, 2 days, 3 days, and so forth. And there's 3 things that are being represented here. So the first one represents the solar flux and our K index. In this particular case, it's A, but it could be AP as well. So this is the X-ray radiation, and this is the charged particles affecting our magnetosphere. The second one talks about a propagation window, again on the same time frame, and it looks at our maximum usable frequency, which comes from the E and F layers, And then we have the lower usable frequency, which is proportional to the excitation in the D layer. And last one is due to the geomagnetic storm itself, which is just noise on the HF bands. If you're trying to pull out an S9 signal and you have S20 noise, it's just, you're not going to hear anything. So assuming that we have a flare at time 0, this happens on the sun, there's a flare right now, we won't know about it till 8 minutes later. That's how long it's going to take photons, whether it be X-rays, whether it be UV, whatever, that's what it's going to take to get to Earth. And at that point in time, they do two things. They start exciting the EF, and if we have X-rays, the D field as well. But also, due to the flare itself, we're going to hear a solar burst that this thing is going to last maybe 30 minutes, 60 on the very outside, but it's usually a few minutes to 30 minutes and then tapers off. So what follows is outstanding communication or propagation conditions because the E and F fields are being charged by the UV and X-rays coming off the sun, which pushes our critical frequencies and maximum usable frequencies up near to past 50 in this example, past 50 megahertz, but certainly above 30. So we can be talking to Southern Sudan, Southern Chad, or I know there's a bunch of you looking for contacts in North Korea. You might be able to get one on 10 meters under these conditions. So that's great up until through the first day, right? Then we have on the start of the second day, maximum use of frequency is coming down, but it's still pretty dang high. 10 meters should be wide open at this point. And it's relatively quiet. Now, by the end of the second day, or towards the beginning of the second day, the charged particles that came off the sun in that solar flare should now be hitting the magnetosphere. And then at that point, our geomagnetic disturbances go through the roof and we have a full-blown geomagnetic storm taking place. Also, what's happening is charged particles are being dumped into the D layer. So the attenuation goes sky high, exceeds that of the E and F layers, causing a blackout. So this will last, if it's a significant solar flare, this blackout on the second day of the storm is likely to cause blackout. Also, we have extremely high noise on the HF bands. And then by the third day, everything starts returning back to normal and normal operations take place. So this is a combination of what solar flares do relatively instantaneously within the first few minutes or within 8 minutes of the initiation of the event, and then how the charged particles traveling at a much slower speed finally catch up and interact with our magnetosphere, interact with our ability to communicate, either by boosting it in the first couple of days or by driving a blackout on the second day. Any questions, comments, concerns?
I have a question.
All right. Yeah, go ahead.
Hey, this is Don, KD4APP. So, kind of going back, I'm going backwards, but if you want to move ahead, I can ask my question later. But what I wanted to ask about was, I do a lot of 20 meter. I have been for the last few months doing a lot of 20 meter F8, FT8, and I noticed that the station count goes down quite a bit at night. So I'll see, all kinds of things but sometime in the middle of the night, I'll be waking up and just seeing very little stuff going on, just mostly local contacts. My antenna is a G5RV. It's definitely at a low angle. It's only about 17 feet high in the middle, and probably 5 or 6 feet out on the ends. I've worked Australia, Japan, all over the place with the thing at certain times of the day, obviously. And obviously there's, I think I'm starting to see some of what's going on with that, for what you explained with the low incident takeoff and that sort of thing. So would it be at night, maybe I needed a higher angle or antenna to use that more, or what exactly is happening there?
So let me rephrase the question. So basically what you're asking is, hey, at nighttime, when I'm on 20 meters, my signal, the signal seems to degrade. I don't get as many contacts as I do during the day.
And I don't receive as many. Yeah. I mean,
okay. So what's happening is the electron density, the ionization level during the day is much more intense than it is at nighttime. There's 2 orders of magnitude difference between 1 to 2 orders of magnitude difference between the electron density during the day and the electron density at night. So what that translates to in English is I have a lower critical frequency at night than I do at day. The daytime, I have a high critical frequency, high maximum usable frequency. But at nighttime, when the electron count is lower, it doesn't refract as well as it does during the daytime. And therefore, sometimes you're just lucky that it's working at all. But it's because of the shift in count of electrons from day to night. This also happens from winter to summer. There's variations in the electron count in the ionosphere, and that goes directly to your ability to bounce a signal off the ionosphere. Does that answer your question, Don?
Yes, I think so. Absolutely. Because I can tune, to 40 meters or 80 meters FT8, and there's lots of activity going on there at that point. So absolutely helps with that. Thank you.
You're welcome, sir. All right. So let me move on. Just one more topic before I get into how do we use this stuff, and that's coronal mass ejection. So these are rare events, but sometimes near the middle of the solar cycle, at the most intense portion of the solar cycle, we'll have aggregation of a number of or pairs of sunspots. And what happens, these magnetic fields become interconnected, and there's a lot of energy that gets pent up and stored in this. If anybody wants to know the mechanism behind it, I'll be happy to talk to you after the presentation's over. But what it does is when these things finally snap, think of it as a giant rubber band that you're twisting. When it finally snaps, there's a lot of energy that's released. And what it does is it rips out billions of tons of material and hurls away from the sun at several million miles an hour. So typically it takes, flares take a couple of days to get to Earth. And here's this image. You see the size of this flare. That's the size of Earth compared to it. You can just imagine the amount of energy that's involved in this thing. If this thing, depending on its trajectory, if it's a glancing blow to our planet, we get to see really cool Aurora Borealis and Australis. In other words, the northern and southern lights will be phenomenal. But if it's a direct blow, we could see massive radio and electrical blackouts due to solar EMP. And John Norris turned me on to this one novel, 1 Second After, or there's another After the EMP. they'll wake you up. And we did have one of these events back in 1859. This was a couple of years before the Civil War, during solar cycle 10, where it was known as the Carrington event after the astronomer that identified it. But they saw northern lights all the way down in near Cuba, and they saw southern lights in Queensland, Australia. And this thing was so intense that it was traveling at a very high rate of speed. And instead of taking the 2.5 days to reach Earth, it reached Earth in a matter of 18 hours. And the effect was impressive. Now, technology-wise, we were dealing with wired telegraphy at the time. So the telegraph systems over northern Europe and North America failed. There were sparks that were coming off the telegraph poles. Telegraph operators reporting being shocked, and some even were able to continue sending telegraphy and receiving telegraphy, even though their systems were off. Had that happened nowadays, it'd be a major catastrophic event. Back in 2012, we had a similar magnitude solar flare, but fortunately, when the sun belched, it wasn't pointed directly at us. Had our orbit been 9 days earlier, we would have been in extremis. So anyways, enough of solar events. So I've talked about all this stuff. Now, how do we use it? So sources of data, like I said, NOAA, specifically Space Weather Prediction Center, has a lot of these data points that we can go look up and then try to put into tables and graphs and whatnot. That's one way of doing it. They also give us, so I didn't talk much about the 70 centimeter radio flux, but that's what's measured for the solar flux. Anyways, that information is available, and that's what gets entered into. What's a lot easier approach is using some type of software. Fortunately, online, we have Voices of America's coverage analysis program. And what it does is, let me move this again, it's right in my way, there we go. And what it does is allows any ham operator logs onto the site to go in and choose two coordinates or two locations on the planet that you wish to make contact, select what your mode of operation is, how much power you're running, your types of antennas. You can input settings such as sunspot number, etc. And then it'll give you propagation charts or propagation wheel. And the propagation chart is this chart that shows you the time of day, UTC, and the percent circuit reliability, meaning the chance of you having a successful contact between 2 points. In this case, I'm showing Roswell and Madagascar this was on the 13th of December when I plotted this. But it shows that 12 meters at 1800 UTC, 15 at 20, etc. These would be the most likely frequencies that I would use to be able to complete this circuit. So let me go to this live, and hopefully I don't end up getting knocked off. That's that video. Oh, so here we go. So I was talking about the data that's available, right? NOAA's Space Weather Prediction Center has all manners of information, and they've got a whole slew of stuff down here. Go through, look at it, play with it. but it's informative, tells you what's going on. So for instance, here we are on the, what is today, the 19th, right? So it's saying that our flux is 77, our planetary index is, our A is 15, our KP is 3, which is pretty dang quiet. It also gives us sunspot predictors. But what I wanted to show is we can take this information and put it into the vocab. And so it's real easy to operate. It's going to ask you if you want to enable the location. And when it does, it puts the red indicator in your QTH, Roswell, Alpharetta, wherever. And then you can figure out where it is that you want to talk to. If you want to go after that North Korean station, or you want to go to Madagascar, there you go. You indicate what mode of operation, in this case sideband. I don't have an amplifier, so I'm going to run 100 watts, and I'm not going to change the antennas, but I'm going to bring up firstly the propagation chart. So you see the propagation chart, it's somewhat different than the one that I'd originally shown you. And you can remove some of these just by clicking on or off the particular band. But what I like even better is this propagation wheel. It's in my mind, it's a lot cleaner and easier to look at. So these are the bands, 10, 12, 15, up through 80 meters, etc. This is UTC, and the color code in the circular graph indicates the percent reliability for this particular circuit, which is Roswell to Madagascar at this point, well, throughout the day. So at 1900 UTC, I've got roughly a 60% chance of making that contact. But if I'm really desperate and I can manage to talk my CFO into springing for an amplifier, then all I did was update that. And as you can see now, between 18 and 19 UTC, now it's jumped up to a whopping 70%. And if I go for the legal limit, then now I'm up to 80%, et cetera. It also, so this is for DX. And if we're looking at, if we want to look at, let me back it up. We're trying, there we go. So it allows us, so if I'm doing near vertical incidence communication, you can zoom in and look at 2 points. And now let me go back to what we would normally have, 100 watts. So it tells me that the later hours of the UTC day, I have a higher probability, but pretty much communicate with Chattanooga any time of the day. I'll have better luck in the evening hours than I would during the daylight hours. But there you go. It's a pretty easy tool to use, and it has a lot of versatility. You can plan ahead. Let's say you've got a contact coming up in this weekend. You want to make sure that you're able to make that contact. What do you have to do to make that contact? So let me go back to my PowerPoint presentation. Keep having to move this bar around. There we go. All right, there's another one. hfradio.org has another one. It's similar. This is not as, I don't find it as useful, but it contains all the same information. It's just in a different format. Others may prefer this to that color wheel that I showed. But what it does is, again, UTC, it figures out what the sunspot cycle is, or sunspots. It tells you what the centimeter, what the flux is. what the ionospheric disturbances are, calculates that, and gives you this. So if you're in the East Coast and you're trying to contact Western Union or Western Europe at 0800 at 0800 UTC, 14 megahertz is as high as you're going to be able to go. So that's another tool. There's also software-enabled tools, but frankly, given what the capability that you have with the Voice of America software, I find this underwhelming. You find it for Mac OS, you can find it for the PCs, etc. But again, I think that vocap is pretty amazing stuff. And lastly, I just want to talk briefly about Cycle 25. And given what we've seen and looked at, we may have to pay more attention to it, given that Cycle 25, the predictions aren't flattering for Cycle 25. They suspect that it's going to be another weak cycle similar to the one that we just had, and with a long minimum, deep minimum, which is what we're experiencing right now. So this is, in a nutshell, everything that I had to present for ionosphere propagation, etc. So if you have any questions, I'll be happy to entertain.
Actually, a comment, Jim, and thank you for the presentation. It was really interesting. There is another model out for solar cycle 25 that presents some opposing viewpoints to some of the models you are presenting, that actually says it could be a fairly strong solar cycle, and we could see very strong, a fairly strong maximum coming up here soon. I heard about it. I listened to the ICQ Amateur Radio podcast, which is it's kind of an international podcast, and a couple 3 months ago, they interviewed a researcher that said that he's got a whole new model. It's been extensively peer reviewed, and it says we may be in for a whiz bang coming up.
I hope so. That would
So
be
do we
awesome
all.
news.
So do we all. I've been stuck at 124 DX entities for about 7 or 8 years now.
So
I have a couple of questions. I'll take my
Yes,
turn
sir.
though.
Go ahead, Jim.
W4QO. But you put me in the turn or take them down, whatever you want.
well, you already jumped in there, so get going.
Okay, let me verify that I don't use that vocap. That's an online system, I guess you'd say.
Yeah,
And,
yeah.
And how do
Yeah,
you
it's-
get it? How do you get it to that page that says vocap for ham operators or whatever? I wasn't clear about that.
So I'm still sharing. So let me get back to that. So it's www.vocap.com /HF /.
Oh, /HF, and that gets you to the ham radio.
Yeah. And
Okay.
as a matter of fact, if you just type in vocap, Voice of America, cap, HF, there it is, vocap online for ham radio.
Okay, very good. Now, throughout all this, I hardly ever heard you say anything about sunspot number. And all my friends are saying, "Oh boy, look at today." I just looked, and the sunspot number is 101 or something. But I didn't hear you mention that much.
Right. So I didn't mention sunspot number, but what I mentioned was solar flux, and the two are pretty tightly linked. But yeah, so solar flux. So I had in my previous presentation, I had a formula to convert solar flux and sunspot numbers, etc. But you're right. Solar flux is directly proportional to sunspot numbers. And as I pointed out earlier, the higher the solar flux, it's actually the higher the solar units. Where is it?
No,
Yeah,
just quiet.
more sunspots, more solar flux, higher maximum user frequency. But yeah, I didn't mention specifically the solar count, but there's a formula. It's
I was looking at the picture.
0.63 times. Yeah,
I didn't see the
0.63
word.
times sunspot number.
Now, what about the A and K index? We want those to be low, right?
Yeah. So let
And-
me go back
and-
to the.
Yeah, and so what do we want those to be low and the sunspot numbers to be high? That
Right,
when I get
so
up in the
we want-
morning, I just want to look at something and see how my day is going to be.
Just look outside the window.
Oh, okay, I forgot about that.
If there's snow on the ground, it's not a good day. But no, so the
Unless
A
you're a
and K,
skier.
right? These are the ones that indicate if they're very quiet, hey, we're not going to have the magnetosphere is not being disturbed. We're not going to have any interfering noise on HF, at least not from the magnetosphere. And if we have high sunspot number, that means high solar flux. That means higher maximum usable frequency, which means DX.
So Jim Kauffman,
Yes, sir.
we have another question. The question is, how can increasing output power raise the circuit reliability? You still have to hear the other guy for two-way communication.
Good point. Well, you're right. If you're blasting legal limit and their QRP, Jim Stafford can speak to this. Probably gone hoarse calling CQ on QRP while the guys on their legal limit amplifiers are just heating up the sky. It's you have to have two-way it's a circuit, two-way circuit. So just because you're running 1500, if the other person's running 1 watt, you might not be able to hear them. So that assumes that bidirectional contact. So yeah, if there's a guy in Madagascar that's only on 10 watts, doesn't matter what size amplifier, he might be hearing me, but I'm not going to hear him or her.
Also, there's a thing you see on QRZ and all that, and it says, sunspot number and this and that, and it has activity on 40 meters fair, 20 meters poor, things like that. I wonder if you could interpret that whole thing for me or for us.
I'm not sure which one you're talking about, but but basically, Jim, what they're saying is that so you said they give the solar flux or the sunspot number. You're muted, Jim.
To see you interpret that. It's all that people, there's some little piece of code you put on your website and it makes that little thing pop up on your website. I don't have it, but I think we have it on our, or we had it on our northfulton.org website on the homepage down at the bottom. I don't know if that's still on there or not. Maybe Bill can answer that if he's still around.
I am, Jim. What were you asking about? I'm sorry, missed that. I was sending a note to somebody.
Well, there was a little square thing about, I don't know how big, 2 by 3 inches that popped up. I'm trying to find it real quick here. It used to be on the bottom of our page and it would say things like your probability, your 20 meters is going to be good. No, it's not. And it's uh, 10 meters is fair and all that kind of thing. We used to have
So,
that on our
well,
homepage.
yeah. Well, I'm looking at it. I'm not seeing it, but basically what it's doing, Jim, is it's interpreting the sunspot number or the solar flux, either one, and it's looking at the geomagnetic disturbances, if any. And as I said, right, when I was given the when I was talking about maximum usable frequency, that only addresses 50% of the circuit reliability. So meaning half the time, half the days, given those conditions, you're actually going to be able to make a contact. So if you want to increase your odds of making a contact between any 2 points, you're going to have to lower frequency so that you're able to refract a signal off the ionosphere. I mean,
Yeah, I understand. Go to qrz.com. It's on the homepage every time. Picture of the sun on there and all kinds of numbers, and then there's aurora and band closed, and there it is. Then you got down there at the bottom, it says,
okay.
you know, poor, fair,
All right.
and all this. Well, I don't know how to interpret all that. I'm sort of simple guy.
Right. Okay. So the solar flux index, right? It's saying it's 77, which I looked at it today and it agrees. That's the amount of it's the amount of ionizing power that's coming off the sun right now in terms of UV and soft X-rays. This is closely tied to the SN, which is our solar number, or sunspot number, 13. A stands for our.
Well, wait a minute. On the SFI, we want that to be high or low, or do we care?
Oh, we want that to be high, right? That's the, if it's over 150, your SFI is over 150, that means 10 meters is wide open and everything else is too. And that's going to correspond to a higher sunspot number.
Okay, now you got the, okay, now you got the A and the K. You talked
the
about
A
that.
and the K, those are related to your geomagnetic disturbance, which is a indicator of how much noise you're going to have on HF. You want these numbers to be as low as possible. K is 0 through 9, so 1 is pretty dang low. 0 would be better, but whatever. And A goes from 0 to 400. 6 is pretty dang low. So what it's saying is that, yes, we have low sunspot numbers. Our propagation is going to be marginal, but we have quiet conditions. So you with some finesse, you should be able to make some contacts. You're not going to make great DX, but you're not going to be drowned out by noise, at least
Yeah.
not magnetosphere.
Okay, now we got all these other numbers on here, and then down to the bottom, it has a.
You mean these?
I mean, yeah, I keep forgetting to press my space bar. Yeah, what? So all we have to do is watch those, or how about it says very quiet signal noise level. That's one.
So this is just
MUF, flares. There's a lot of stuff on there.
Right. So what this is, Jim, is this is just a in plain English interpretation of these numbers up here. So our 77, our flux, sunspot number, etc. It translates to on the 80 to 40 meter bands, it's fair. At nighttime, it's good. 20 and 30, and not so good. Your higher frequencies, definitely not good. Right, that geomagnetic field was 6 and 1. It's very quiet. So that's what that's talking about. And solar flare probability, it's pretty low, 2.4. And then if you're going over the poles using either Aurora or Sporadic, that path is not available. It's the conditions don't exist.
Okay, thank you much. I appreciate that. And I don't have to worry about looking at the sun then, you know, that picture. You know, right? I mean, well, I don't mean outside. I mean, there's a picture of the sun on here and I'm, you know, I don't need to worry about that, I guess.
You're not supposed to look at the sun. It's going to hurt your eyes.
I didn't mean that. I meant that little picture there is what I just ignore that.
Thank you for the prompting.
Thank you for your explanation. I appreciate it. There's all these numbers on there and it's kind of hard to figure out at times. Thank you. A good presentation.
Thank you.
I had one other comment.
Go ahead.
Okay, this is Don again, KD4APP. I was just wondering, and I appreciate the presentation. It answers a lot of questions. You know, I've done satellite work. I've done, you know, a lot of VHF, UHF when I just had a technician license. And since I've got my general, I've started doing more HF. So this is all great. I just recently got into microwave also, 10 gigahertz. And there are a group of people, mostly in the Midwest, that are doing rain scatter and snow scatter. So they're enhancing their signals by bouncing it off of rain and snow. Have you seen any of that? There's a site called rainscatter.com that does some predictions.
No, I have not. Yes, I'm aware of it. I'm aware of the phenomena, but no, I've not looked at that. And so that might be material for another day.
Absolutely. All right. Thank you. Great presentation, though.
Okay, so it's 9:12, and unless we have any other questions, I just want to let you know that this presentation will be, it's been recorded, and probably towards the end of the week, we'll have it up on YouTube so that you'll be able to go see it if you want to review anything. I think we want to thank Jim Kauffman very much. So you all raise your hand or give him a clap or send him a free lunch ticket or whatever it is you want to do. Thank you, Jim, for your presentation tonight. It was great.
Jim,
Thank
that
you.
was an excellent presentation. You answered a lot of questions for a lot of people, made it very simple to understand what they're talking about between day and night and different effects. So it was excellent.
Well, thank you. And thank Jim for reminding me to go take a look at the little explanation there that's readily available.